Good. So yeah, this is going to be a pretty big talk because we're going to try to cover everything from astrochemistry to emerging worlds in 12 minutes. So normally when I think of these two topics, the sort of common theme is astronomy. These are things we study with astronomy or astrophysics. And now we wait. Yes, all right. So if you think about the circle of life, a lot of biologists, geologists in here, but for astronomers, the circle of life is something very different. Stars explode, material is blasted out into the ISM, it then coalesces again into gas clouds. These clouds start to collapse, you form a protostar and a disk around it. This disk starts to segregate out, you form distinct bodies, comets, meteors, and obviously planets. You deliver material to the planets, and then you start to form habitable worlds, and eventually you get to life. But this is a very big and complex topic, so we're going to go through some of these stages one by one. So the first one is the Astronomers' periodic table. So this is scaled by the abundance. So the bigger the square, the more abundant it is. So if you're an astronomer, most of your world is hydrogen. Almost all of the universe is hydrogen. There's a decent amount of helium. And then the metals, oxygen, carbon, nitrogen, silicon, iron, make up a tiny fraction, and then everything else, so the interesting things like phosphorus that are required for life, is this tiny square down here at the bottom. Oxygen and carbon are a factor of 10,000 down from hydrogen. The metals are even further down. And the dust and ice, the solid parts of the universe, are only about 1% of the observable mass. So this is very different than what we're used to. And it's actually a very strange place. So most of the universe, the diffuse ISM, is atomic, so most of the matter is just hydrogen atoms. All of your carbon is ionized, and there's a decent amount of electrons. As you go to more dense and dense regions where the gas starts to shield itself and there's less dissociation, you actually start to get neutral carbon, and eventually you transition into heterodiatomics, actual molecules. But it takes quite a while, and this is actually most of the ISM. So the way the dust and gas sort of follows is it starts by coalescing into a dense cloud, and then it'll start to collapse. So this is about 10,000 AU across. So an AU is the distance from the Earth to the Sun, so it's enormous. This is our start. This is our start point right here. After about 10,000 to 100,000 years, the gas starts to collapse. You get a star forming in the center, and you get an envelope around it that slowly starts to fall in, and you get a disk in the center with a star. So this takes a few thousand years, and it starts to collapse down to only a few hundred AU, so starting to look like a solar system. Then we move on to the protoplanetary disk phase. This will take several 100,000 to a few million years to complete, and now we're actually on solar system scale. So this is when the gas collapses down into a flat disk around the star. It then starts to segregate into planets, and eventually we end up with a solar system. And this takes somewhere in the neighborhood of 50 million years to complete. So astrochemistry mostly takes place in big gas clouds. So once things are ejected from a star, they're mostly atomized or solid pieces of dust, and we have to build everything back up to the big complicated molecules we see in meteorites and comets today. So the mass is something like 10,000 to a million solar masses. It's enormous, and most of the mass doesn't end up in the solar system. It's just it's remnant dust. It's a few hundred parsecs across. The density is tiny. It's only 100 molecules per cubic centimeter, and it slowly ramps up to maybe a million. For reference, the air we're breathing right now is 10 to the 19 molecules per cubic centimeter. So it's we cannot make a vacuum here on Earth that is as good as anything in space. It's incredibly diffuse. And the temperature starts at about 10 Kelvin and slowly ramps up as the star turns on. So astrochemistry is sort of an interplay between three things. Laboratory astrophysics, where we take spectra, measure things we need, either spectra or kinetics for understanding what we see. Astrochemical modeling, where we basically create models of how chemistry is going to occur in the ISM. This lets us understand the observations we see and feeds back to giving us new species to look for, reaction intermediates, things that could lead to more interesting things like the building blocks of life. And then observational astronomy is where we do our version of lab work. This is where we're actually going to go out and observe things. We'll get abundances, distributions, temperatures of molecules, understand what they are, where they're going, and get some ideas of how they formed. And this all sort of feeds back together, and slowly we start to build up an understanding of the chemistry that's happening. So the chemistry that happens is actually not like anything you'll see on Earth. Things like H3+, H3O+, C2H5+. Most of the gas phase chemistry happens through ions that that are extremely difficult to make in a lab. And we do all of our work detecting them almost exclusively with radio astronomy. So far, we have identified 180 molecules, give or take, in space. See, most of them are 1, 2, 3, 4 atom. Almost all the big molecules that we've detected have been through radio astronomy, with the exception of C60 and C70 buckyballs. And so the interesting thing here is, one, as they get bigger, they get much more difficult to detect. You see the 2 and 3 atom ones are actually pretty easy, but as you get past 6, things start to get very difficult. And the other really interesting thing that's come out of astrochemistry in the last couple of years is that anything more complicated than about methanol, anything 6 atoms or above, generally has to be made on a grain surface. Reactions in the gas phase can make a certain set of molecules, but the big molecules are extremely difficult to make unless you're on an ice. So the way this generally works is you have little silica dust grains that are floating around. They condense a few layers of ice. And then you can think you accrete one molecule, another absorbs onto the surface, they roam around and find each other and make molecules. And this is the way we start to build up all of the big molecules. So the amino acids, purines, pyrimidines, things that you see in like the Murchison meteorite, all have to be made through this process. After that, we move on to the protoplanetary disk phase. All of the material that was made in the ice and dust is accreted into a flat, sort of flared plane around a protostar. So this is sort of a couple cartoons of what that ends up looking like. So you have a central star. As it turns on, it blasts all the material around the star away, so there's a big gap, and the material is accreted through magnetic accretion there. As you move out, you get thick layers of dust, and so you get a series of complicated processes. So you have vertical and horizontal mixing that takes matter from the top of the disk down and back up, and then horizontally towards the edge or back towards the center of the disk. The edges of the disk are extremely warm, as is the front of the disk, but as you move to the center, it cools down. This is where all your ice and dust are going to be, and this is where small bits of dust will start to stick together and form bigger and bigger pieces that eventually become planets. So understanding this is extremely complicated, and this actually ends up determining a lot of your inventory for the planets, meteorites, comets that you're going to see in a planetary system. And one of the big keys here is where the snow lines form. So as you move further and further out, water freezes out first, then CO2, then eventually CO, and then eventually you start to drift into interstellar space. And so where each one of these forms is going to determine a lot of the condensable matter that's available to be put into a planetary body. So this has a huge effect on the solar systems that'll come out of it, and has a huge amount. The gradients you see are very much determined by the star in the center and the total mass that goes into this. So one of the really cool results that's come out very recently, this is the Atacama Large Millimeter Array has finally imaged a protoplanetary disk. This is sort of brand new science that's being done. This is actually, believe it or not, the first time we've ever really observed a disk that has gaps in it. So we've always known that somewhere in the transition between a disk to a planetary system, you have to form gaps, small bodies start to form, you get less emission, and eventually they have to become planets. But we've never seen it before, so this was actually really amazing. And so the really cool thing is if you look at where there is less dust, so red is more dust emission, the dark spots are where it's not that we've lost the dust, it's that the dust is stuck together. So now the surface area that can be emitting is much smaller, and you're starting to form icy bodies. And if you plot these rings where we've lost emission, they match up perfectly with the ice fronts for water, ammonia, and just larger hydrated minerals. So all of the chemistry that's happening and the physics of the disk are basically readily observable here, and you can start to see how this affects the entire solar system. And so from here, what's going to happen is it's a very complicated process, but now we have a solar system that's evolved from a large cloud of preplanetary material. All of this is driven by chemistry that happened in the cloud. Almost all of the condensable material is formed in the cloud as it heats up and as it collapses. And so what's going to happen is now you've formed a planetary disk. All the planetary bodies that existed have now condensed, and now you enter the debris disk and heavy bombardment period. So now you have planets, and now we start delivering organic material to them from the disk that was formed. And this is going to provide the feedstock for the planetary system. So this is how things like Earth get their water and their organic material. This is where Murchison comes from, and this will be the starting point for evolving life on a planet. All right. So, questions?
All right.
Some people talk about the lack of source of energies for formation of some molecules based on temperature, but as you mentioned, there are they may get formed in stellar conditions and then transferred to somewhere else, or there are cosmic rays. Which effect is dominant? Because based on papers, and when you read papers, it's just they're talking about temperatures and they're trying to model the same conditions based on temperature. But as you said, there are a lot of sources of energies, and then they can get energy from there.
Yeah, so this is a lot of stuff I glossed over, but just even in a disk, so you have UV and X-ray photons doing a lot of work on the edge of the disk, but you also have cosmic rays so for those of you who don't know, cosmic rays are just high energy particles. They can be electrons or protons, things like that. So the cosmic rays are always present. We know they have to be doing some of the chemistry, but it really depends on where you're talking about. If you're talking about in a dense, cold core, when the star hasn't turned on, then cosmic rays are a dominant source of energy for the system. As the star turns on, if you're close to the star, obviously temperature gradients are going to drive a lot of the chemistry, UV photons, so it really depends on where you're talking about. But all of those are very valid sources of energy. It just, the dominant source changes depending, because remember, we're going from several, tens of thousands of solar masses down to a few hundred to make a planetary system. Most of this, it's huge orders of magnitude scaled process. So it really depends on where you are.
So we always can get energy for the reaction?
Yes. Yeah, there's always some source, whether it's enough to drive
even
big,
if it's cold region or...
In a dense, cold cloud, you generally don't have a ton. You have the outside is externally irradiated by UV photons, but cosmic rays have really low cross sections. They'll penetrate very far into a cloud. So there's always some source, but it changes very much depending on where you are.
Okay, thanks.
Awesome. Great warm-up talk, Brandon. That was great. You said that we can't make a vacuum on Earth that is anything like that of space. Could you throw some numbers at that? I'm trying to wrap my mind around what a vacuum would be in the dispersal of molecules versus the vacuum of space. And
the vacuum of space, especially if you're talking the really diffuse ISM, is like 10 molecules per cubic centimeter. Trying to think, we are at 1 atmosphere right now, and that's 10 to the 19. We can get down to a few hundreds of thousands, millions of that, but we're still orders of magnitude away. It's actually it's really difficult to pump all the hydrogen and helium out because they just keep coming back. They're tiny and they're really difficult to get out of a system. So they're really, yeah.
Wow.
Yeah, many orders of magnitude. It's impossible with so much crap around. Everything finds its way back in eventually. It's really tough.
Wow, that was fantastic. That was my big mind-opening moment of the day. So.
Hi, Brandon. Over the end of the talk, you mentioned how protoplanetary discs are responsible for the chemistry of life on Earth.
Well, the disks are remnants of the original molecular cloud. So the inventory there is at least partially driven by what happened in the cloud as it collapsed. And I mean, this is a dynamic process, so there's a lot that goes on even in the protoplanetary disk phase. Yeah.
Okay, but you mentioned that is responsible for what we see on Earth, the chemistry on Earth.
Well, it's feedstock. It's your starting point.
Okay.
So let's see if I have this tucked somewhere away. Yeah. So if you look at the D to H ratio, the protostar is the D to H ratio is the sort of interstellar 10 to the minus 5. Earth is up here, 10 to the minus 4. And all the cold, icy bodies in the outer solar system tend to have D to H ratios much closer to Earth. So the assumption is that the water has to be made early on. In fact, there's a good science paper by Ilse Cleves. Like water is one of the big things you need to, well, at least we think, make life on Earth. And that likely has to come from the outer solar system during the heavy bombardment period, at least partially.
All right, and you also said just before that that you are now able to see protoplanetary disks.
Protoplanetary disks in this detail.
So can you get to the chemistry of these disks and perhaps
we're working on
judge?
it. Right. So there'll be some talks about this today, but this is pushing the world's best interferometer to its absolute limit. So this is a continuum image. So basically, they're just bending every channel together. You have to actually resolve the spectra to see molecular lines. And so to make images of a protoplanetary disk where you can actually sort of image, say, CO or methanol or something like that is going to be really tricky. The next couple decades will be really exciting for that. But yeah, it's sort of right on the edge of what we're going to be able to do.
I see.
Probably not at this resolution, though.
All right. Thanks.
All right. I think we need to move on to the talks. Let's thank Brandon again.